Hey you guys, this is Mr. Millings, and in this video we are going to learn how to calculate equilibrium concentrations. So let's take a look at our very first example. In this first example we have H2 gas reacting with I2 gas to produce 2 moles of HI gas, and it says right here that we need to calculate the concentrations of all 3 substances when 0.250 moles of hydrogen gas and 0.250 moles of iodine gas reach equilibrium in a 1.5 liter container, and it tells us the KEQ for this chemical equilibrium here is 25.0. So if we take a look at this chemical reaction, we're given the number of moles of hydrogen gas and we're given the number of moles of iodine gas, and we need to figure out the equilibrium concentrations of each one of these substances in our equilibrium here. So first thing that we have to do is we have to figure out the concentrations of H2. So we have to figure out the concentration of H2, and we need to figure out the concentration of I2 that we're starting off with. So in order to do this, it says that we have 0.250 moles of H2, and we have 1.5 liter container. We also have 0.250 moles of I2, and this is also going to be placed in a 1.5 liter container. And so the concentration of hydrogen gas is going to end up being 0.167 moles per liter, and the concentration of iodine gas is also going to be 0.167 moles per liter. So the first thing we did is we figured out the concentrations of the substances that we're starting off with. And so now that we know this information, what we can do is we can rewrite this chemical equation. Okay, so let's go ahead and do that. In this chemical equation here, if we take a look, we have H2 gas reacting with I2 gas, and this is an equilibrium with 2 moles of HI gas. So what we now need to do is set up an ICE chart. And ICE stands for initial change and equilibrium concentration. So let's go ahead and do this. We have I, C, and E here. And if we take a look here, the initial concentration of our hydrogen gas is right here. It's 0.167. And the initial concentration of our iodine gas is also 0.167. And the initial concentration of this is going to be 0. Initially, we don't have any HI gas, but we have 0.167 moles per liter of this and 0.167 moles per liter of this. And so now, this chemical reaction is going to take place, and there's going to be a change in the concentration of H2 and I2 as it produces HI gas. And so we can label this change as negative X here, negative X here. And if we take a look at the stoichiometric relationships between these substances here, this right here will be a positive 2x, right? The concentration times the coefficient here of 2 we put right here. And so at equilibrium, what is our concentration going to be of hydrogen gas? Well, it's going to be 0.167 minus X. The concentration of I2 is also going to be 0.167 minus X. And the concentration of our HI gas is going to be 2x. So here is our ICE chart. And so now what we can do is we can set up our equilibrium expression and solve for the concentrations of each one of these substances. And so in step 3, we'll label this as step 2, And in step 3, here we go. The equilibrium expression for this chemical reaction, or chemical equilibrium here, is going to be products over reactants. And so we have the concentration of HI squared, because of coefficient of 2 here, divided by the concentration of H2 times the concentration of I2. And so we can just simply plug in these equilibrium concentrations now and figure out our answer. So it tells us KEQ is 25.0. So we'll put that right here. 25.0 is going to equal the concentration of HI. So what is the concentration of HI? Well, it's 2x, and we're going to end up squaring this. We're going to divide this by the concentration of H2, 0.167 minus x, times the concentration of I2, 0.167 minus x. And so we'll do the rest of this problem up here. And so this looks like we're going to end up with 25.0 equaling 4x squared all over 0.167 minus x also squared. And so now, what can we do here? We're going to try to solve for x here. And so what we can end up doing is we can end up taking the square root of both sides. If we take the square root of both sides, we will end up with 5 here, equaling 2x over 0.167 minus x. So let's go ahead and break this down and solve for x. We're going to cross multiply here. And when we cross multiply, what we're going to end up with is 2x equaling 5 times 0.167 minus x. So 2x is going to equal 0.835 minus 5x. If we add 5x to this side and to this side, we're going to end up with 7x equaling 0.835. And if we divide both sides by 7, x is going to equal 0.119. So, now what we can do in our last step is use this x value to determine what the concentrations at equilibrium of each one of these substances is. So let's go ahead and do that. And so if we take a look, what is the concentration at equilibrium going to be of our hydrogen gas? Well, let's see here. For our H2 gas, the equilibrium is going to be 0.167 minus x. So 0.167 minus 0.119. And we are going to end up with a concentration of 0.048. If you take a look, the equilibrium concentration of hydrogen gas is the exact same thing with our iodine gas. So iodine concentration at equilibrium is also going to be 0.048 moles per liter. And to figure out our HI gas concentration, we're going to take 2 times x. So 2 times 0.119, and we're going to end up with 0.238. So, what are all 3 equilibrium concentrations going to be? If our KEQ is 25.0 and we're starting off with 0.25 moles of hydrogen gas and 0.250 moles of iodine gas, reaching equilibrium in a 1.5 liter container, well, if you take a look, the concentration of H2 is going to be 0.048 moles per liter. Iodine is going to be 0.048 moles per liter, and our HI gas is going to be 0.238 moles per liter. Let's take a look at another example. In this second example, we have C2H4 gas plus H2 gas in equilibrium with C2H6 gas, and what we want to figure out here is we want to figure out the equilibrium concentration of C2H6. So once equilibrium has been reached, we want to know what the concentration of C2H6 is going to be. Furthermore, we know we have 0.75 moles of C2H4 gas and 1.50 moles of H2 gas placed in a 2.75 liter container, and we know that KEQ is equal to 9.83. So the first thing that we have to do is we have to figure out the concentration of C2H4. And we have to figure out the concentration of H2 gas. So, if we take a look, we're given the number of moles of C2H4 gas, and we're given the number of moles of H2 gas, and we're given the volume of our container in liters. So you guessed it, we can figure out the concentration quite simply. We can calculate the molarity. So we have 0.75 moles of this in 2.75 liter container. We have 1.5 moles of hydrogen gas in 2.75 liter container. So we'll get our calculator out. 0.75 divided by 2.75, and we end up with 0.273. 0.273 moles per liter. That's the concentration of our C2H4, and we'll take 1.50 divided by 2.75, and we're going to end up with 0.545 moles per liter of H2 gas. And so what we now have to do in step 2 is we have to rewrite this chemical equation here and come up with an ice chart. So in step 2, we see that C2H4 is reacting with H2 gas, and this is in equilibrium. And our product is C2H6. So we have to start with our initial concentration, the change in concentration, and our equilibrium concentration. And so if we read this question, the initial concentration of our C2H4 is right here. It's 0.273. The initial concentration of our H2 is right here. It's 0.545. And the initial concentration of this is going to be 0, right? We're starting off with these two reactants, and we don't have any of this stuff yet. So what is the change in concentration going to be? Well, we'll go ahead and label that X. In other words, this substance here is going to start to be consumed to produce this stuff here. So the concentration of it is going to start to disappear by some amount, and we'll call that X. And same with our H2 gas, minus X. And if we take a look over here at our stoichiometric relationships, if we take a look at these coefficients, then this right here is going to gain, or concentration is going to start to increase by positive X. So our equilibrium concentration of C2H4 is going to be 0.273 minus X. This right here will be 0.545 minus X, and this right here is going to just be X. So here's our little ice chart that's going to help us solve this little problem. And so if we take a look, let's go ahead and figure out our equilibrium expression in step 3. In step 3, KEQ here is going to be the products over the reactants. And we don't have any solids and liquids here, it's all gases, so all these need to be included in our equilibrium expression. So we're going to have the concentration of C2H6 all over the concentration of C2H4. Times the concentration of H2, and you'll notice that we didn't need to add any superscripts here or exponents here because the coefficients here are all 1. So now what we can do is we see that our KEQ value is 9.83. So 9.83 is going to equal the equilibrium concentration of C2H6, which is simply X, all over the equilibrium concentration of our C2H4, which is 0.273 minus X, times our equilibrium concentration of H2 gas, 0.545 minus X. And so we're going to do the rest of this problem over here. And let's go ahead and do our algebra here. And so we have 9.83 equaling X over 0.273 minus X times 0.545 minus X. And so this is going to equal 9.83 equaling X over, and if we go ahead and distribute all of this stuff here, we take 0.273 times this, and then 0.273 times negative X, and negative X times 0.545, and then negative X times negative X. We're going to end up with 0.149 minus 0.818x plus x squared. And so if we cross multiply, it looks like we're going to have x equaling 9.83 times 0.149 minus 0.818x plus x squared. And when we distribute the 9.83 to each one of these, we're going to end up with x equaling 1.465 minus 8.041 x plus 9.83x squared. And so now we're starting to see that this is starting to look like a quadratic formula, right? We have x squared here, we have x here, and we have a number right here. So let's go ahead and figure the rest of this out. If we subtract x from both sides, what we're going to end up with is 9.83 x squared minus 9.041 x plus 1.465 equaling 0. And if we take a look, this definitely fits a quadratic formula, right? Where this right here is A, this right here is B, and this right here is C. So this looks like a quadratic equation where we can use the quadratic formula to solve for x. And so that's what we need to do in our last step. So in our last step here, we're going to use the quadratic formula to solve this little problem right here. So in step 4, let's go ahead and do that. In step 4, we know we want to solve for x right here. Then x is going to be equal to negative b plus or minus the square root of b squared minus 4ac, and this is going to be all over 2a. And so now what we can do is we can start to plug these numbers in. Negative b, well, if we have negative 9.01, that is going to be 9.041. Sorry, not 9.01, 9.041. Plus or minus the square root of b squared. If we take negative 9.041 and we're going to square this, minus 4 times A, which is 9.83, times C, 1.465. And this is all going to be over 2A, so 2 times 9.83. And so when we put this in our calculator, we're going to end up with 2 answers because we see right here we have plus and we have minus. So we're going to end up with 2 answers. We're going to end up with a final answer of 0.210, and we're going to end up with a final answer of 0.710. So which of these 2 answers here is going to be the correct answer? Well, if we think about it, if it's 0.710, if we take 0.273 and we subtract 0.710, we're going to end up with a negative concentration, and that just can't be. So this right here is not going to be our correct answer. So what is the concentration of our C2H6 once this system has reached equilibrium? It looks like the concentration of C2H6 is going to end up being, so the concentration of C2H6 once this system reaches equilibrium is just going to end up being X. We just figured out X. X equals 0.210. 0.210 moles per liter. So that's how we can use the quadratic formula to solve for equilibrium concentrations. So if you like what you guys see, go ahead and click that little bomb in the bottom right hand corner, and that's going to subscribe you to my channel. And I really hope you guys found this helpful.